I'm gonna do some live streaming of Haskell today, programming some LLVM. Yeah, need to get used to my live stream setup again because it's been a while. But today I will be porting over some C code that I have. That's shown right now on the screen, and I will be porting it over function by function to LLVM. I will in no way get to the end, but I think it's interesting to see how it all works together. So yeah, let's get started. So the last function I did was this one. Use this as an introduction because this function here and also this function here, those are all very similar, and I think we can refactor a common part out because each one of them checks if a node is of type leaf node and then returns a specific thing, and otherwise it will do a loop over all the children and it will call some function. And so I wrote this one now, and then in a second we will refactor that and then reuse that same logic here. So in LLVM it looks like this, or well, in Haskell, and LLVM, gets strange. But here we have some helper functions to give me back the LLVM type based on a Haskell enum kind of thing. So if I go here, I can ask for these things and I will get an LLVM type back. Where was I? And then here we can just make a function. This is the name that will end up in the LLVM code. You have your function arguments, you have return type, and then you have some arguments in the block of code. And inside the block of code, that's where we actually write all this stuff. And basically here we check what is the node type of this node n. If it is, and I think I made the convention if the boolean, because this returns a boolean. If the boolean is true, then it's an inner node, and otherwise it's a leaf node. If it's an inner node, it will jump to this block, and otherwise it will jump to this block. And then, as we can see here, the depth is 1 if it's a leaf, so we just return 1 here. And if we have an inner node, then we need to loop over all... wait, I'm looking at the wrong function. If we have an inner node, then we need to... we just need to find a child, because what I'm building is a B tree, and it's balanced, so every child has children, potentially, but all the nodes are they're all at the same depth. So we just pick the first child, calculate the depth based on that, and then we just add 1 for the current node. So that's also what happens here. We cast to the correct pointer type. We find the child at a specific location, and in this case we always find the first child because it doesn't matter. And then we call the function that we are defining. So this is how you do recursion. And then we get the depth of the child back. We add 1, and then we return that. That's the entire function. But next step is to refactor this and then reuse it for the node count and also for actually we need to check here as well if some code can be reused. But basically I just explained how one of the functions work. In a second we will be building another function, but let me first check if the stream is properly working. I think so. Okay, so Let me move this one to the top. Oh yeah, okay. So in this, yeah, this function, we can't use this one, but we can use the counting function, because in both this function and the one below, we have some data, we loop over something and then we collect all the results basically. So let's start refactoring it. So basically this part is the loop, and here we allocate the first value, and then yeah, we need this entire block, I think. And then at the end we need to get the final result back, and then we can return. So I think we can just copy this entire thing. Let's call it loop children. Don't know the type yet. It will we will figure it out. And so now here, yeah, this counting, this needs to be refactored because this will just be a generic result. This will be a certain type. This will be a certain begin value. And yeah, those are both parameters here. This inner node thing. Yeah, so let's just pass in n, and then this line also needs to be copied. Maybe we can figure something more elegant out in a second. And then we need to copy this line. And so let me see. We allocate the begin value. We figure out the number of elements so we can loop over it. Then we start with a for loop from 0 to the number of elements. We increment the counter with 1 each time, and here is the counter. Then we find the child. One by one we find all the children in the array. And then, here, this needs to be changed. So this is the current result. And then, okay, so how do we call this then? Child result. Yeah, it's a bad name, but we can just call this f. That needs to be passed in like that. And then the updated result, and So what I think we need to do is we need to refactor it like this. So we get the current result, then we get the current child, and then we calculate some updated result based on a function. This line needs to be moved, and then I think here we need to pass in also the current result. So this is like the accumulator in FP functions. And then here we get updated results, and then here this is the result, and the return needs to be removed here. And then let's save it, and now it will horribly break because we need to give it a type. Here we have the begin value is an operand, the value n, that's also an operand, and then we have a function, and then we have our monad that also eventually returns an operand. Okay. Yeah, let's put this on multiple lines like this. And then here we get operand, and then ir codegen operand, like that. I think this is result. Okay, that compiles. So let me check what I wrote down. So we created a function loop children. It takes a type and a begin value. Those two work together. Then we also pass in a node. That's the one where we want to loop over the children. Actually, maybe we should move this one to here. I think that makes more sense. But then this becomes... Yeah. Okay, so here we have our node being looped over, basically. And then for the loop, we have a type and a begin value. And excuse me, and then we have a function f that combines each time the current result, that's this first operand, and then the new result, and that will again give us a new result. And each time in the loop we always fetch the current result that's stored somewhere on the stack. We call the function and then we store it again. And we keep on looping and looping, and then at the end we load it back one final time, and that's the end result of the loop. And now we need to refactor this whole thing. So, so let me make some space here and then comment this part out. So we definitely need a return instruction at the end. That's why I'm placing that there. Don't know why my cursor moved. Anyway, now we can say loop children. What's the node? It's n. And then we start with i64 and then with the value 1. And then now here we get yeah, that's basically the accumulator, and then the child. Let me see if this type checks. Okay, that's already good. Also, this returns a function, so this is called the count. So here we can return the count. Yeah, and now we need to check which lines can we delete. So let me move this in screen if it fits. So the bitcast, we have that already. We have to allocate this. Yeah, inside this return. Yeah, we have that. That's this line. And then this entire part, do we have to store? We have to deref this and the for loop. So I think this is it. That's all that remains. That's nice. Okay. What's the current node count? Oh. Oh boy. That's neat. So we loop over the children of this node. The value is of type 64-bit integer with value 1 at the beginning. And here we get the node count and the child that we iterate over. And then for each one of them we call count nodes, and we add the node count to the child node count. That's nice. And then yeah, that at the end you could even just say this, it will still work, I think. Oh, it's probably has to do with parentheses. This is fine. Just move it a little bit like this, and then group the blocks a little bit together. Let me check the stream. I haven't used Twitch in a while. I already forgot how to use it properly. I'm sorry. This can be removed, I think. Still compiles. Do we need this? We do need that. Okay, yeah, that's fine. Let's see on the right side. So here we have the entire assembly, which is much bigger than what we have on the right side. Okay, this is gonna be quite complicated. So this is saying start from this node parameter and figure out the pointer with indices 0, 0, 3. That will end up finding the node type. Well, this is a pointer, so we need to load it, and then based on that it will either go to count inner 0 or to count leaf 0. If it's a leaf, then the node count is 1, that's correct. If we go to count inner, then we need to cast the pointer type. We allocate the count that we start with, and then so we allocate one of them of type i64, and then here we store the value 1, and then here we ask for the number of elements, and we load that value from the pointer, yes, and then we go into the for loop, and then either I is 0 if we come from the this previous block, or it's %14, which we will see later. That's probably the end of that's the incremented I value of the for loop. Then here we check, this is like the for loop condition, like is it smaller than the number of elements, and if it's smaller or equal to, then it will jump into the for body, and otherwise it will go to the end. If it's inside the for loop body, it will here it will load it will load the current value of the count. Then it will find a child at a certain position. It will fetch that child, then it will call node count on that child, and that will give us back the node count of the children of that specific child, and then you add that to the current node count, and then we store that back into the value, and then we add, here we increment I, and then we go back to the beginning of the for loop, and it keeps on looping until we hit the end. And then here here we load the final count and we return it. Oh boy. And this on the right side, this is so much more complicated than on the left side. And this is it's still complicated, but it's doable. It's more high level, easier to read. And we can keep refactoring common pieces of code out, because right now it might have seemed complicated, but with the next function it will become more clear. So the next function is node entries. So can I copy this? Probably have to copy it like that. That also works. Let me copy a few functions, and we'll see how far we get. And then we can close this. So let's make the next one. Make node count entries. And we generate code at the module level. Yeah, with this recursive do extension, you can create loops really easily if you don't watch out. So be careful with that. Let's see. Yeah, so I just noticed here we also do we check the type, and based on the type we will do one thing or the other thing, but I'm not gonna refactor that yet. Maybe later, but for now it's, yeah, that doesn't make sense yet. So let's just write the function. So we need this, count entries, and at the end we do this, just to make a type check, and then this is a function, node count entries. Hang on a minute. I just noticed my title is wrong. Oops. Let me change that real quickly. Boom. Anyway, where were we? So again, this takes pointer of type node. That's all the same compared to the last function. Oh, and also let me plug it in here. Oh, already. I already defined it before the stream, my bad. This is better. Let's see. So we need to copy this part, and then also this part, and that part. Okay. It does start to look fairly repetitive, but it's really hard to not to refactor it. Okay, so if you have a leaf node, that's the easy case. We need to find the number of elements. Okay, so num elements is deref of, we need to find the metadata, and then we need to find the number of elements of n, and then we return num elements. Okay. And then here, so, and if we look here now, this line is the same. Okay, this initialization, that's different. Then we have the same for loop with the exact same conditions and everything. The only thing that's different is this function here. Okay, so only thing I need to do that's different here is this needs to be the number of elements, I think. Yeah. So since I need it in both branches, then I can delete it here, and then I can add it there. Maybe even do it like that. And so first we ask the number of elements, then we ask for type inside the node, and then we then we branch into two different directions. If it's just a leaf node, then we return the number of elements. If it's inner node, then we need to do something like this. So we need to loop over the children for the specific node, and we here we need to say, yeah, this becomes number of elements prime, and yeah, I need to add it because I will explain this in a second. Let me first type it out. We need to. So here it goes number of elements, and here goes the type. So the thing is, number of elements, that's a 16-bit integer, but yeah, LLVM is not happy with that. We need to make it 64-bit because because at the end this function also returns 64-bit. And let's see, so this is an entry count, I guess. And then this part is not count nodes, but it is count entries. So we call it for each of the children, and then the entry count. This is almost exactly the same compared to before. I think the only thing that's different is this part here and this part, but I'm not sure if refactoring will help that much because it's only two functions like that. So let's see. Okay, that was that. Oh, can't type. So now we have a few easy functions, but they have to be written. Let's see. So node, type of node, and then function node is empty. That returns Boolean, so that's a 1-bit integer. Okay, and so now we need to num_elements is deref of meta of num_elements n. Okay, so now we have the number of elements, and now we need to say is 0, and then num_elements like that. Okay, and then okay, and we can probably write this simpler like this. Okay. And I need to generate the code for that and delete that. The loading is starting to take quite a long time, even with GHC IDE. So that's something else to look into soon. So that was this function. And now a very similar one. Node is full, and then yeah, that's still correct. And then num keys. So yeah, I'm taking a look at the C code below here. But this is going to be a problem. So, let's keys, number of keys is this, and this is a word 64, so we need to make it an integer. Is that possible? Oh. Okay, and now we need to make it an int16. Oh, and we need to generate the code for it. Yeah, so okay, that still was fairly doable. It was just a lot of conversions, so maybe let me add this here. Okay. We're actually going quite a lot faster than I thought we were going, but I guess that's a good thing. In the beginning it went a lot slower because I didn't have all these high-level functions like dref, and I built those a few days before this, and it just helps so much. Okay, so node split point, and right now I'm returning unit for all of these, but at some point they will return the functions themselves so that you can call them from each other. But for these simple ones, it's not needed yet, so I'm not bothering with it yet. Okay, this one is going to be a little more tricky. It has a lot more mathematical calculations mostly. Let's see. So we need to say node split point. Oh, and it takes no parameters. That's also interesting. And that returns a node size t. That's do I have that type? I do. So let's see. Oh, that's annoying. So I can use this type, but and I can use it in the return type, so I will use it, but I can't use it when I'm creating my variables. Oh well. Okay, so we need to do this same thing here also. Okay, and then now we can say A is multiply tree with number of keys, and then let's call this A prime then, and then here div int 16. I think it has to be like that. I need to check the instructions in a second anyway. Okay, and that one is just subtract. So b is subtract of number of keys and in 16.2. Okay, and then we need to return the minimum, and the minimum is a macro, but we can turn it into a function kind of thing. So minimum, no, let's call the function minimum, but let's call this result, and then minimum AB, and then return results. Or we can combine it again. And then here we can say minimum takes an operand, another operand. Yeah, probably don't need that, but oh, that's an import thing. Number of keys, why? What? Oh. Okay. Yeah, we need to build the minimum now, and that's this macro defined here, so variable names is hard. A less than B feels bad. Is less than, okay. A unsigned less than B. So if A is less than B, then result is select if A is less, then A is the minimum, otherwise B, and then we return this. Oh no, we just need to do this. Yeah, the thing is, if here we return, if we do an actual return, it will also automatically put a return here and then another return, and that's bad. So this is it. Okay, let's see. We don't generate this code yet, so oh, non-exhaustive patterns in a lambda. Oh. Yeah. Let's see. So, what does this thing do? So, let me check. First does a multiplication of 3 times 15, that's the number of keys, that's correct. So this is just 45, and then it will divide that by 4, it will be 11, I guess. But I still want to have a function for this and not have this be a magical constant. So here we get 11, and then B is just, we subtract 15 and 2, and then it will take the minimum, so that will be 11 or 13. So yeah, 11 will be the final result that is returned. Yeah, but the generated code looks fine, so you can also remove this part. We're going much faster than I thought. Okay, let me maybe first make a commit. Bad commit message. Follow over some more functions to. Well. Okay. Let me go back to the B tree code. So where were we importing it over? We were here. Oh, and yeah. Now begins the real challenge because the functions will start to become bigger. That's going to be interesting. Yeah, okay. We still have 15 minutes. Let's give it a shot. This will probably be the last one on the stream. So, make split. Module codegen. And do this, and then yeah, let's first include this thing. Okay. Oh, that's interesting. In the C code we have an assert, but we can't do that here, I think. Let me open the browser. I am that's something to figure out later, but I will put it to do then. Oh, and now that I'm checking it in my browser anyway, this fdiff, is that what I think it is? Or is it udiff? Or is it hasdiff? Oh boy. This always takes a long time. Must be integer values. So I think it's this one. Oh, it's so slow. So I think udiff is for unsigned and sdiff is for this is signed integer quotient, and this is the unsigned one, and this. Aha, yeah, that's the wrong instruction. Good thing I check. So this is udiff, that's fixed. And then here to do how to do assertions in FVM. Okay, so we can't do that. Let's just paste it here, and then let's create a function again. Function node split, I guess. I called it split before, but that's not a good name actually. And we need a pointer to a pointer of a node, and it's called the root node. And then here we get node n and the root. add type nodes, type of nodes. What is it complaining about? Oh, need to add a return type, I guess. What is this thing? Returns void. There we go. So we have a signature now, we have this, and now split point. Okay. Split point, then we call the split point function. Call node split point takes no arguments, but we need to add it here. That's also an operand. And then now we do need to start passing around some functions. What's going on here? Oh, need to go here. This returns an operand now. This pure, we delete it. Okay. So we have our split point. So this can be deleted, this can be deleted. Let's port over the comments. Oh, interesting. We also need the node new function. So we get sibling node new. Oh, we need to call that, and then need to give it the type. So the type and then some no. So we first need to extract the type. Then we need to pass it in here, and then we give no function attributes because that's not needed now. So let's see, we need the type. Okay, dref meta of and then node type of n type. Is that correct? I think so. So we have a sibling now. Oh, this needs to move underneath the comment. Now we need to do a loop. Oh boy. We have a loop with two variables, but my loop so far can only handle one. So I think I'm gonna use a stack-based approach here, and hopefully LLVM will optimize that. That's something fun for me to check after the stream. Let's see. Okay, and so it copies over all the values one by one. Interesting. Okay, so first of all, that value j, that's a 16-bit integer. Okay, so allocate and starts at 0, and then we loop over. Oh no. We need a different loop here. We need loop values. I didn't build that yet, but we will have to in a second. We will loop over the values. And then we get a value here. So let's just write some pseudocode. And then for each of the values, That's annoying. We need to loop over both the the sibling values and the node values. Okay, then we can't do this. Then we need a raw loop. Let's see, for loop. Then we start at 0, and then we say inside less than number of keys, and then here add int16 1. Okay, and then here we get I variable. Nope, wrong direction. Let's fix all the type errors. Hey, hello. How are you doing, Barry? What time is it where you live? Probably some lag on the stream. 4 p.m. Oh, that's not too bad. Yeah, I'm good. Thank you. I think it's been a few months since I last did this, so I'm getting the hang of it again. But yeah, I'm good. Thank you. Where was I? Let's see. Yeah, so we were building the for loop. And then, oh, interesting. Split point plus 1. Okay, so let's call that split point prime, and then add 16 1 to split. Like this. And so our for loop starts from split point prime. Yeah, and then yeah, I am really pumped about this. It's so powerful. It's amazing. Like you can keep refactoring and using combinators, and you start really slow with just low-level instructions, but you just keep on building and building on top of each other, and now I feel like I'm going faster than in C, which is kind of ridiculous with just pure LLVM basically. And yeah, in Haskell you do all the meta programming. So yeah, and on Twitter I posted some examples of how far you can take it. You can like rebuild fold-L on top of just LLVM code. That's crazy because you have very little overhead compared to in Haskell. I got sidetracked again. So so we allocate j with 0, so that's this part, and then we say I less than number of keys. We also did that part. Okay, and at the end here we need to say here we need to load j. So this is like a pointer, so j is load 0 of j pointer, I think, or is it flipped around? So the ultimate goal is, hang on. So what you are saying, that's a possible goal, to write some really low-level Haskell libraries that are super efficient. But my real goal is to build a data log almost entirely in Haskell. But I want I want to base it on Souffle. But that's, Souffle works with C++. That is all string concatenated together. And I think there's a better approach, and that better approach is to use llvm for it. So right now what I'm doing is, yes, eclairs are delicious, hence the name. So what I'm doing differently compared to Souffle is I am generating llvm code. It's a lot more type safe, it's a lot more composable. And I think it will be a more maintainable implementation. Well, that's my theory at least. And yeah, this is one of the last parts. So I already have an interpreter working, and now I need to finish up the runtime, and then I can compile it so that it calls the correct runtime functions. But yeah, all the high level stuff, I already did that, or I at least have a good idea on how to do it. This is like the last piece of grunt work, I guess, I still have to do before I have my MVP working. So yeah, that's the ultimate goal. Oh man, you really need to start digging into the data log stuff. It's so powerful. I'm gonna write some helper functions for load and store in a second, because I keep forgetting the order. Let's see. Oh, I'm confused by this one. Let me remove that. So, I think this is J pointer. Yeah, then a 0. Yeah, then here let's call it this, and then J is at 64. Oh, no, that's also a 16-bit. Okay. So yeah, this part is a little bit annoying, and I'm hoping llvm will remove the load and store. But we'll see. Okay, and so now this line is the last part I still need to do. I need to copy over all the values one by one. Okay. Let me see. I have a value at value at. Yeah. Oh, and this part has to do with the blog post I wrote yesterday. That's also really cool. Some of the llvm stuff is like really low level or a little bit unsafe, but with Haskell you can just program in that, make everything super type safe, and then you don't have to think about it anymore. So what this is saying, this is a path from a node to a value. And hang on a minute. Otherwise I would have to keep writing down all the indexes one by one each time, and that gets so tiring, so let's not do that. So let's see. Sibling value pointer is a value dref value at and then Oh, we need to watch out. So on the left side it's J, but here it's I. Okay. So here goes the sibling. So then we get the sibling value, and then we need to assign the value at I for node n, and then we need to assign. Wait, this is the actual sibling value, and then here we need to assign that. Whoa. Let me check this, because this is tricky stuff. I don't know of other people building it in this way, which is kind of unfortunate. I still, yeah, I think this is like, yeah, not explored enough. I said something similar when I was presenting the data log stuff, but this also is unexplored. I think there are a few people using it, but yeah, I don't know them, and they are probably using it for very different things, because yeah, LLVM is so generic. You can use it for a lot of stuff, and I'm using it yeah, to just port over one big C file, and yeah, who knows what other people might be doing. Yeah, so yeah, I don't know. But I am probably going to be giving a talk about this, because it's so fascinating how far you can take it. Because yeah, like you can generate your function here on the fly, and then maybe JIT compile it, and then call it from Haskell, and then you have like a super optimized version. You can do really crazy stuff with this without too much trouble. Because I've been doing the LLVM stuff for like a week or so now, and the instructions are low level, but you also get the hang of them quickly. So yeah, then it becomes really powerful. So you can expect a talk somewhere in the following months. Let's see. Where was I? Oh, I was checking the assembly. Yeah. So we can see here that it is loading a specific value, and the value is like a few, like one value is one data log record, basically. So multiple columns of the same type. Yeah, don't want to go too deep into details, but yeah, this is just a data log fang, basically. We can load it, that's stored in here, and then yeah, the offsets here are different. So this is the J variable, yeah, because we load that here, and then this one, that's the I variable calculated here. So we load from J and store into I, and also the node parameters are different, so that seems to be correct. And then inside did I do that part correctly? Then we store yeah. We store this value in this address. Oh man, that gets really difficult to read. But thankfully we have these helper functions. So yeah, that's that part. So that was quite complicated, and then we're not there yet. Okay. So now we need a part if we are an inner node, because then we also need to copy, or we need to do something with the children. For that I also had an helper function. Is it like this? I'm not sure. I think so. Yeah. Do we have the type yet? We do. So is inner, then the type equal to like this? No. Okay. So if is inner, and so you can see I have built many control flow constructs, so I don't have to think anymore about raw instructions. So I have this helper file that I didn't have to open yet, and here I have helper functions for allocating one thing, many things, copying stuff, assigning, dereferencing, and so on. Wait, hang on a minute. Yeah, oh, sorry. I was just double checking the instruction. But I have all these helper functions, but also I have stuff like a for loop. And this for loop is, yeah, it's quite complicated to build the first time, but yeah, I don't have to think about that anymore. I can just give the begin value now a condition, which is just a function. Give it a post condition, or like like the increment part of the for loop. I can just pass that in as a function, so it's all really high level. And then I have like the inner assembly, which is again a function, so it's completely inversion of control to the max. But yeah, because of that, I don't have to think about looping and stuff anymore. It's just all handled for me now. That's so nice. And it's the same thing with this one-sided if branch, because this is similar to when you write in Haskell when some condition do blah blah blah. But yeah, at some point you run out of words, so I just was lazy and added a tick to it. Let's see. Okay, so what is happening in this part? So we cast a sibling to an inner node, okay, and we cast a node to an inner node, okay. Then we loop over. We do almost the same loop, except now here we have less than or equal. And then we assign to the children and update the parents. Okay, this is going to spit out a lot of assembly when we're done, but that's okay. So let's call it iSibling then to stay consistent. Sibling bitcast to a pointer of inner node. We don't have that yet. Type of inner node. Whoa, where did it jump to? And then here we cast the node. It's called n here. N is bitcasted also to an inner node. Okay, then we have that part. Then we have a for loop. So that's this part again, basically. Oh. Okay, yeah, we need to use a different name, I guess. Or we can reassign to J. Is that okay? Yes, it is, because in the last loop the j went out of scope. Okay, so here we don't allocate, but instead, so let's first indent it. Then here we say store. This is a 0. Let's move that. And yeah, it's a little untyped sometimes. So both holes are an operand right now. And now, yeah, this is something I still need to figure out how to remember that. And so for that I already built the assign instruction or combinator, but yeah. And it's defined like this. So first you have the address. So that would be the j pointer, and then here you say int16 0. Okay. So I guess it's the same as in a normal programming language. First pointer and then the value you assign to it. So this can be removed. And let's move this up and then comment these 2 lines. And then let's see, what do we need to do? So we need to find the child of both the sibling and the node. Okay. Let's see. So the difficult part now is the children are defined as follows. No, where is it? Hey. So the children, that's an array of node pointers. So yeah, this is going to be a complicated part. But first things first. Sibling child, and then dref child. Am I saying that correctly? Yeah, I need to watch out a little bit. So this is quite complex stuff. So let's first ask for the child. So that's child at location I of the I node. Yeah, and then we need to assign that to child at j of my sibling, and we assign the child. Oh boy. So now we did this line. And now we need to continue. So apparently, so we are moving over. So we have this tree and we're moving values from one node to the other node. So if you move a child, then you also need to update the metadata. And that's what's going on here. So I can directly update it here. So, but that's a pointer. Yeah, this is making my brain hurt. Okay, assign, and then the meta of, and then the parent of I child. And what do we assign? We assign the sibling. Yeah. And then we assign the meta of non-elements of the child, and we assign, oh, just J. Okay. Okay. And then, so here we first ask for the child, and then we dereference that, and then assign the sibling to the parent of the child. So this is basically moving the pointer in the tree from one place to another place, and then each child also knows how many elements it has, so that also gets updated. And then we assign the child to the sibling. Poor. That's I'm gonna put it to do here just to check it later, but I think this is it. So now we have that part. Yeah. That was the end of the if. So now we're back at this level. And now we need to say, we need to update the current node. So we assign meta of non-elements of n with split point. Oh, but now we need to, okay, that's the one before incrementing. So we have that line, and then assign meta of non-elements of the sibling. And here we get, wow. Sibling num keys, that needs to be defined. So sibling num keys is so we subtract number of keys with split point, and then we need to do another subtract. Can we combine that? No. Huh, that's annoying. So sibling num keys sub sibling num keys. Yeah, and this is where the assembly gets a little bit annoying, but it's doable. Like that. And what's it saying now? Oh. And we have number of keys already? Oh, we do. This is a monster function, by the way. So let's see, yeah? This was the last line, then here we say number of keys minus the split point, yeah, and then that value minus int16 1. Okay. Actually, this makes me wonder, can you write this also? That would be cool. But I think you need to do this then. Does that work? No. That's that's too bad. We tried. You can probably use flat map. Yeah, the assembly part, it can be tricky, but if you look at like the node depth function. It's not that bad actually. Comparisons, that's just one instruction that's the same each time. Return is also always the same. The hardest parts are dereferencing the pointers and calculating all the offsets, but yeah, I solved that problem a few days ago. So yeah, to make it type safe, I mean, because yeah, there you have to use like there's like a gap instruction that calculates it all for you, but it's yeah, quite low level. So I made a Haskell helper for that. And all these other things, they're actually quite doable. Like if you need to add, the instruction is called add, so it's really easy. And also, do I have it open? I think so. So like this entire file on Hackage, that's basically all the instructions you can have. And okay, there's like quite a few, but this is it. And so far I haven't needed all of them, so I think it's fine. It took me a few days to learn it, and yeah, now it's it goes really fast. But yeah, sometimes like with the subtractions, you can only do a subtraction of two numbers at a time. So if you like in C, you can just say this minus that minus that. Yeah, you need to split that all up into pieces, and that's a little bit annoying, but it's fine. Yeah, you should, man. Start with an interpreter. It's really easy. Like yeah, maybe build a small language and then build an interpreter for that small language, and then you can be done. Yeah, the first time it's complicated because you have to figure some stuff out, but yeah, once you get the hang of it, writing an interpreter is super easy. And writing the compiler, that's what I'm doing right now. That's the hard part. But if you start with the interpreter, then it's easy. What is this old code? It is. So delete it. So we did that line, and now there's one thing left. Now we need to call grow parents with n root and sibling. What? Oh, yeah, that probably, yeah, that can return an operand, but we don't want that, so we return pure. Okay. So like that, and now we have a small problem because we don't have grow parent yet. Yeah, and is that the next function? That's the question, but I think so. Oh, and I can recommend crafting interpreters. If you follow at least the Java part, that's where he builds the interpreter. You could try porting that over to Haskell, and it will be probably much shorter. And the other comment was, yeah, you can probably use the bind operator for it. But then you also need to flip it, because, yeah, I will try that out in a second. I did read structure and interpretation of computer programs. Well, if you want to build a language, so I think both books are great, but if you want to build a language, I think Crafting Interpreters is better. But Structure and Interpretation of Computer Programs, that book helps with the stuff I'm building right now, so that you build abstractions on top of other abstractions and so on. So yeah, the comment with the sub thingy, where was that? That wasn't that function. So I will try it. It's here, right? And then we remove this, and then this result needs to be piped into this at this location. So we need to flip it like that. That's it. That's yeah, you're welcome. Yeah, so this works, but yeah, at some point the readability goes down. But yeah, I will leave it like this for now. So yeah, let's see. So I'm looking at the C code right now, because we came so much farther than I was expecting, actually. And grow parent is the next function. But as you can see, the functions are starting to become larger and larger, and that's not a coincidence. This is where the meat of the B tree is taking place. The good thing is it's all just assignments of stuff, so that's really easy now. It's just a lot of work. So I think I will continue this off stream. But one final thing I want to do is I want to yeah, I want to check the assembly that comes out. So let me make a placeholder. Like this. And then function node grow parent, and then yeah, I don't know. Oh, I do know the arguments because they're listed right there. So the first one is a pointer to a node, then a pointer to a pointer of a node. That's the root. And then the sibling, and that's another pointer to a node, I think so. And then here we get n root sibling. Oh boy, what a line. Let me move it like that, and then this needs to be returned. And so this is the cool part about recursive do. So this right now, this breaks because grow parent is after make split. But if you put mdo here, it should be fixed. Yep. Oh, I need to fix those things in the placeholder I'm defining. So node type of nodes. What is it complaining about now? Can I just put pure here? Oh, I need the return type probably. What's the return type of grow parent? It's void. Yeah. Oh boy. So the function that we wrote, it's massive. It's this entire thing. That's yeah. Wow. And yeah, this is stuff you can't write by hand anymore. And yeah, also the code on the left side, that's also a lot, but it's much more higher level. Well, much more. It's higher level. So, and yeah, you just need to keep on piling abstractions on top of abstractions with combinators in the case of Haskell. And then at some point you have like good primitives, and then you can start building this stuff out really, really easy. So let me check the assembly. So first we call node split point, yeah. Then we add one to get the split point prime, yeah. Then let me, yeah, since this is the last thing I'm doing, let me change the file type. Might be easier to read, I don't know. So what does it do then? Oh yeah, then it calculates the pointer to the type of the node, and then we load it, and then we call node new. That gives us back a sibling, and then we allocate the j pointer, and then we store 0, and then we go into the for loop. Well, we go into the first for loop. And we start with what? Is that correct? That's bad. So let me check that. So block names. Let's see. Huh. Okay. So if you don't have a block name, then it just picks the first instruction. That's okay. Yeah, well, we're explicit now. Anyway, where was I? So here it builds the for loop. This is just the condition check, and then goes into the body or to the end. And then what's going on here? Okay, so it loads the j value. Yeah, and here we have this dereference and assign stuff. So that's the load and another load and then a store. Wait. No, this is the load of okay, this is strange. So this is j. And okay, and so this is sibling value. Okay, and here we store into the node value. Poor. Yeah, and then we add one to j, and then we add one to I. And then then the loop goes back. And then at the end of the loop, then we are here. Then we check, is the type equal to 1? Yeah. If it's equal to 1, then it goes inside the if, and otherwise it goes to the end of the if. And then we have the if. And then here we do 2 bit casts. That's correct. Then we store j. We store 0 in it again. And then we go to the for loop, the second one. And let's see. Let's move that a little bit more up. So then the second for loop begins, and then it goes into the body or it goes to the end, and then here this is the part where we load j again, and then we load, that's this line, we load the child. So we see the child is a pointer to a node type, and then we assign the parent. That seems to be correct. And then we assign the number of elements. That's another value. And then we update the child of the sibling to be the newly updated child. Then we add j, we add I, and then we go back to the beginning of the second for loop, and then if we hit the end of the for loop, then we jump to the end of the end if block. Man, this is a big function. And then we are at this part. So now we do a few more assignments. So this is the assigning of the split point. And then the two subtractions, and they seem to be correct. So you have 15 minus some value, and then this value and this variable minus 1. So that was a good suggestion. Thank you. And then we're almost there. What's the next thing it does? Oh yeah, so it updates the sibling num keys after we calculated it, and then we call node grow parent, and then we return. So yeah, you can see how complicated this becomes. So it is possible, but I prefer the version on the left, and I actually am starting to almost prefer it compared to the C version. I think there are a few helper functions that I still need to define, but we're getting there, and I'm refactoring not too soon, but after I discover some patterns. So this is it's quite a big task, but it's a lot of fun. So but I think I'm gonna quit here for today. So thank you all for coming. And maybe I'll do another stream in a few days. I don't know yet. But thank you all for coming. Bye.